Hey, welcome to another episode of our 15-minute Friday session. This week, you look across the country, we are in a extreme heat wave regardless of what corner of the country you might find yourself in today. But what I want to talk about specifically is Polyon and also how that relates to performance under these specific kinds of conditions in the hottest parts of the summer. But before we get into that today, it's important to talk about, how do we define fertilizers? How do we talk about fertilizer classifications as it relates to not just Polyon, but all fertilizers? We know that if we're talking about pesticides, we're talking about fungicides, herbicides, insecticides, that those products are regulated by the Environmental Protection Agency or the EPA. We don't have a federal group similar to that to regulate fertilizers. Instead, we rely on a group called the Association of American Plant Food Control Officials, Association of American Plant Food Control Officials, or APFCO. And APFCO is a board of state regulator leadership that defines fertilizer classifications and guides the state regulations on a state-by-state basis. So these folks get together a couple of years. They talk about different definitions. They talk about different types of fertilizer technologies that may be coming to the market and how they can classify those and how that they can discuss or how we can label those products so that they are in the marketplace at least represented accurately for what they are. And so when we're talking about Polyon specifically, it is classified as two things: an enhanced efficiency fertilizer and a controlled release fertilizer. So enhanced efficiency fertilizers are fertilizer products. This is per the AFCO definition. Fertilizer products with characteristics that allow increased plant uptake and reduce nutrient losses to the environment when compared to an appropriate reference product. A controlled release fertilizer, Polyon is defined or fits within two classifications per AFCO. A controlled release fertilizer is a slow release fertilizer that is engineered, and that's a pretty important word to me at least, engineered to provide nutrients at a predictable rate under specified conditions. So you start to unpack this a little bit. You say engineered. This is a material that we create in our manufacturing facility. And because we have that level of control over it, it's going to give a predictable rate of release under specified conditions. So what is an ideal controlled release fertilizer? Each granule is coated with a homogeneous layer of polymer, a homogeneous layer of a coating. And this coating gives the characteristics of consistent release, predictable release, and controlled release. And importantly, what we're going to focus on a lot today is this polymer provides a high level of resistance to damage so that the nutrients can retain their controlled release characteristics through all of the disruptions that fertilizer may undergo during its life cycle. When you think about it, a fertilizer from the time that it's manufactured to the time that it's coated, to the time that it's blended, to the time that it's shipped, to the time that it's applied, each one of those provides an opportunity for the polymer coating to be somehow disrupted. And if the polymer coating is disrupted, then the nutrient release is not going to perform as predicted. And this is important for controlled release fertilizers because in a lot of cases, we use controlled release fertilizers. We use Polyon because we want to be more efficient with our operations. So instead of a traditional fertilizer application where you may apply half a pound of nitrogen per 1,000 square feet, in many cases with controlled release fertilizers, you're applying up to 2 pounds or even in some cases up to 3 pounds of nitrogen per 1,000 square feet. And you certainly, if you're going to apply that high of a rate of a nitrogen load, you want to make sure that release is going to occur over an extended period of time. Otherwise, your turf grass is going to perform very poorly. So let's look at this homogeneous polymer coating. This is a photograph of Polyon itself. So we have a urea substrate. I'm going to use urea as an example a lot today, but we do coat other substrates as well. But in this case, you see the urea substrate, which is the white material here, and it is coated by a homogeneous layer of a Polyon coating, of our polymer coating. And the thing that I want to point out with this photograph is that you notice the nice tight adhesion and actually a chemical bonding of the urea substrate with the polymer coating. You don't see any gaps in between the urea substrate and the polymer coating. And that's very important for consistent release, but it's also very important for the durability of Polyon as it goes through the shipping channels and application channels. So as a comparison, this is another material that's actually out in the market and has a different technology altogether, has a different chemical makeup altogether, but you have a urea substrate, you have a polymer coating, but what you don't have is the perfect adhesion around the nutrient substrate with the polymer coating, and in fact that you have these small air gaps. And those small air gaps, that gives you an opportunity for disruption to the polymer coating, which will lead to unpredictable release of the coating. And I'll show you a data example of that here in a couple of slides. But looking again at coating durability, just to reinforce some of the different things that a fertilizer blend goes through from the time that you apply it onto your sports field, onto your golf course, onto your home lawns or commercial lawns, is that this material has to go through a blending process, has to go through a bagging process. It's shipped to our warehouses. Once it's shipped to our warehouses, then it's shipped to your place of business. And then finally, it's shipped from your place of business on your trucks or on your gators or on your utility vehicles to where the material is actually going to be applied. And then, the material is finally applied. So each one of those steps provides an opportunity for the coating to be disrupted and the nutrients to release in an unpredictable rate. So we actually test this in a lab. We use what we call a drop test, where we take a Polyon sample after it's been manufactured, and we drop it either 3 times from a height at 20 feet, as indicated by the photograph on your left, or we drop it 5 times from a height of 6 feet on the photograph on your right. And what this mimics is a disruption or possible disruption through the shipping channels, through the handling channels of Polyon before the time that it reaches you. And so we want to look at the data and what this looks like. This is on the vertical axis here on the data. You have percent release on the vertical axis. And then on the horizontal axis, you have time in days after the drop test. And so we're just observing release after the drop test has occurred. So we're looking at 2 different materials here. Polyon is represented by the green lines, and a different material is represented by the red lines. And what you want to see is that there's a nice tight correlation, there's a nice tight trend between the release of a material before drop and after drop. So before drop, that's the material fresh off the manufacturing line, has not gone through the drop test, and that's represented by this solid green line. So that's Polyon just after it was manufactured. In comparison, the dashed green line, this is Polyon after it's gone through the drop test or the abrasion test. And you'll notice that there is a very tight correlation between the before drop and after drop results. You see a slight variation or slight deviation here 10 days after application or 10 days after the drop test. But relatively speaking, that's a pretty tight correlation there. Opposed to another material, this is represented by the red line, where we have the before drop measurement, which has a nice release curve to it, and then the after drop measurement, which is a drastic change or a drastic increase in release speed versus the before drop measurement of this material. So this is not what you want to see. So as this material goes through the shipping channels, it goes through the application process, it's not going to perform the same in the field as it performed off the manufacturing line. Whereas in this case with Polyon, you can count on Polyon performing the same in the field as it does on the day where we manufacture it in our facility. So how does Polyon actually work? Give you a quick run through here. This is again a urea substrate. The green is representative of the polymer coating. Water moves across the polymer coating. It begins to dissolve the nutrient substrate or the urea substrate. Once the urea is dissolved, then the osmotic pressure that is created inside of the prill starts to push the nutrients to the outside of the prill in a process that we call osmotic diffusion. Nutrients move from a low concentration to a high concentration. So they're moving from a high concentration inside the prill to a low concentration into the surrounding soil area. And this process continues until all the nutrients have been released. So there are some fertilizer technologies out there that if you apply them as a slow release material, you might only get 80% of the nitrogen actually releases in a given growing season. Whereas the Polyon technology, if you apply a pound, you're going to get a pound of nutrient release during that growing season. So the rules of release, without going into too much detail with Polyon, is that as temperature increases, release speed increases. As coating thickness increases, release speed decreases. and excess soil moisture does not increase release speed. So here we are, the hottest time of the year. You turn on the morning news and all they talk about is how hot it is in every corner of the United States. You know, there's several parts of the United States that are experiencing daily temperatures over 100 degrees Fahrenheit. Many of us are over 90 degrees Fahrenheit for high temperatures on a day in, day out basis. So how is a material like Polyon going to perform under those hot conditions? So point out, I will note that as coating thickness increases, I want to reiterate, as coating thickness increases, release speed decreases, that is something that we control during the manufacturing process. So if we want a material to use in the heat of summer that's going to release a bit slower, then we can create a material with a thicker coating so that release is going to fit the expectations, regardless of what those expectations may be for your specific agronomic program. So this isn't just one product. This is a family of products that can be tailored to suit your specific agronomic needs. So again, just to reiterate how hot of a period that we're in, this is a map that I took from the National Weather Service today. You can see that these are the high temperatures ending Saturday, July 23rd. So this is for tomorrow. This is the forecast. You see the temperature range here on the top of the image, to where dark red represents 110 degrees Fahrenheit, yellow is 90 degrees Fahrenheit, and the majority of the country is at least in this 90 degree Fahrenheit range, unless you're in the most northern tiers of the United States or you're in some mountainous regions or coastal areas of the United States. So we have a tremendous amount of heat going on currently. And so you might say, okay, well, if his release speed increases as heat increases, then certainly that may not be good for my turf. And that's not necessarily the case. So this is a research trial that we did with Dr. Zhang at Virginia Tech. We wanted to look specifically at how turf responds to different types of Polyon or different coating thicknesses of Polyon when applied under, quote, ideal conditions and then under heat stress conditions. So we had two different growth chambers that we used for the trial. Growth chamber number 1 had a day-night temperature of 72 degrees and 61 degrees Fahrenheit, 65% relative humidity, and creeping bentgrass turf, so very ideal growing conditions for bentgrass turf. Growth chamber number 2, on the other hand, was a bit more of a death chamber. So 100 degree Fahrenheit day temperatures, 82 degree Fahrenheit night temperatures, again 65% relative humidity. In addition to the heat stress, we also induced, or Dr. Zhang also induced, some mild drought stress into growth chamber number 2 as well. The actual treatments that were applied were either the control, which was 0.15 pounds of nitrogen, spray applied using a 28-18 soluble fertilizer applied on a 14-day interval, Polyon 43.5 mini applied at 1 pound of nitrogen per 1,000 square feet as a single application at the beginning of the trial. 43.5 mini is our thinnest coated material. It's our fastest releasing material. And a final treatment being Polyon 41 mini applied at 1 pound of nitrogen per 1,000 square feet. Polyon 41 mini, as far as our mini size products go, these are SGN 120 to 150 type products. 41 mini is our slowest releasing material because it's our thickest coated mini material. Again, the thicker the coating, the slower the release. The thinner the coating, the faster the release. So 43.5 will be fast, 41 will be slow. But let's look at the results. So here on the left, the photograph on the left, you have the non-stress conditions. So these are the 72-day, 65-degree night temperature conditions, well-watered conditions. And you actually know that the 41 mini, the release is actually pretty slow under these conditions. So you're not getting the ideal greening response that you would want to see. A bit better greening response with 43.5 mini. So again, a thinner coating is going to release quicker under these cooler conditions. And then again, the control, which was receiving a soluble fertilizer application at 0.15 pounds of nitrogen per 1,000 on a weekly basis. In comparison to under the heat and mild drought stress conditions. So again, this is 100 degrees Fahrenheit in the day and 85 degrees Fahrenheit in the nights, and also drought stress conditions. But what you'll notice is now Polyon 41 mini under these conditions, creeping bentgrass turf, is providing exceptionally high turf quality, great turf color. Same for 43.5 mini, great turf color under these hot conditions. And then also getting a nice turf response as well from the soluble fertilizer. But again, with the soluble fertilizer, we're having to go out and make an application on a 14-day interval, whereas these two treatments on the right, 43.5 mini and 41 mini, these are single applications made at the beginning of the trial, and that's all they received for the duration of the trial. But the shoots only tell half the story. Let's also look at the roots. And certainly on the non-stress conditions, as we would expect with creeping bentgrass, we had significantly greater root mass as a whole under the non-stress conditions, regardless of the treatment. But what was fascinating in this trial is that under the heat and mild drought stress conditions, that we actually had the greatest root mass with the fastest releasing nitrogen material. So that's not necessarily what we expected at all, but lots of times with research, we find conclusions that counter what we would have our expectations be at the beginning of the trial. So at least in this trial, we were unable to document any negative effects of any of these fertilizer applications compared to the non-treated control. And in the case of 43.5 mini, we had both a positive turf response and we had a positive root growth response under these heat and mild drought stress conditions. And so just to summarize the trial, Dr. Zhang, his comments, in summary, Polyon 43.5 mini and mini 41 had better leaf color and higher chlorophyll content than regular fertilizer applied biweekly, especially under heat and drought conditions. He went on to say that Polyon mini 43.5 and mini 41 enhanced root viability under stress conditions. So certainly Polyon holds up under heat, it holds up under stress, and continues to help your turf perform at its highest level under these challenging conditions. And so I'll wrap up today just to bring to your attention as well that there's many products on the market that are marketed as, let's call them 45-day products, 90-day products, 120-day products, 180-day products, whatever that may be. But that is under laboratory conditions. It's important to realize and important to understand that these materials are all going to perform differently based on your specific environmental conditions. And so with that in mind, we've built a program we call Polygraph. Polygraph takes 30 years of your historical weather data based on your specific geographic location and marries that with the data set that we have created that lets us or informs us of how different polyon coating thicknesses will release under a wide range of growing conditions, specifically under a wide range of temperature conditions. And so we can take those two pieces of information, those two sets of data, enter in an application date, enter in your specific polyon blend, and we can predict how that polyon blend is going to perform in your specific area on any given date with any given application rate, timing, etc. And that's performance that we guarantee with our Polyon guarantee. So if you're interested in learning more about Polyon, it was a very quick discussion today on Polyon. I encourage you to visit our website, polyon.com, or you can also visit us at harolds.com to find your sales rep and to get in touch. Appreciate your time. We'll see you again in a few weeks for another episode of 15 Minute Fridays.